In this video, we're going to be evaluating the limits of rational functions. A rational limit is a limit involving a fraction where we have one function on the top and then we have another function on the bottom. So p of x is going to be a polynomial and q of x is also going to be a polynomial. So our first step is we are going to attempt direct substitution before we try anything else, which means you just plug in the value. So for example, if you have limit of x approaches 2 for x squared plus 1 over x plus 3, that's going to be 2 squared plus 1 divided by 2 plus 3, and we get 5 over 5, which just gives us 1. Now this worked out, and this is going to be our value that we're going to be approaching. That is our answer. Now, if you have a substitution where you get a number over a number, and your denominator does not equal to 0, that means you're done. Now, your second step is you want to check for indeterminate forms, which is when you have a substitution that gives you 0 over 0. That means that you are indeterminate, which means that the limit might exist. However, you need to check first. Now, our second rule is if we get 0 over 0. This means that you have some choices. You can either factor, simplify, and then you can check substitution again. It might just not be in the right algebraic form. Now, your third step is your factoring. When you factor, you can try different methods like greatest common factor, difference of squares, trinomial factoring, and also sum and difference of cubes. So the rule is you want to factor everything before canceling. Common factors in your numerator and denominator. So you only want to cancel the common factors. For example, if you have x minus 2, x plus 3, x minus 2, we're going to cancel x minus 2 and we're left with x plus 3. Another rule is you can only cancel factors. Don't cancel terms. An algebra move that people sometimes make. Crossing out x's is going to be illegal because if you have x squared plus 2x, that is equal to x times x plus 2 because you factor out that x in each term. So you always have to factor first. If you have x plus 2 over x, you have to cancel out the x that way, and then you'll be left with x plus 2. So then you're going to attempt to substitute again after simplifying. Now, you always want to check if you have a 0 denominator. Which means after simplifying, you get the fraction where your numerator is not 0 and your denominator is equal to 0. This is going to mean that the function blows up. But this does mean that you can check the left side and also check the right side. Just because the value that you're approaching is going to blow up doesn't mean the left and right won't. So you can still check for presence on the other sides. Now, if your denominator is equal to 0, but your numerator is a non-zero value, you have to check for this one-sided behavior. So let's look at some cases. Let's say we have both sides go to infinity. For example, positive infinity and positive infinity for left and right. We're going to get positive infinity overall. Now, case 2 is if we have opposite infinities on either side of our function. We have positive infinity and negative infinity. So this is going to not exist. Now, our big outcomes are either going to be number 1, we just get a normal number like 5. Our second outcome is we have positive infinity or we have negative infinity. And then our third one is that it does not exist. So case 1 is going to result in positive infinity or negative infinity, depending on if they were both positive infinity, or if they were both negative infinity. So those are our 3 examples of what we could possibly get. Now let's actually start to try some of these functions. So for our first example, let's do the limit as x approaches 3 for x squared minus 9. We have x minus 3 in the denominator. Our first step is we're going to try direct substitution. So we're going to try to substitute 3 in for all our values of x. We have 3 squared minus 9, and then we have 3 minus 3. That's going to give us 9 minus 9, and here we're going to get 3 minus 3, which is 0. So we get 0 over 0. And this is an indeterminate form, which means we have to do one of our strategies, which we're going to start with factoring. So x squared minus 9, we can simplify that to x minus 3 times x plus 3. And you always want to write this limit x approaches 3 for each part, because that stays. You can't just cut it out and then add it back in the beginning, or at the very end. So you have x minus 3 here. You have a common factor, so you can cancel those out. And then you get limit of x approaches 3 for x plus 3. So now you can just do some direct substitution because our denominator is no longer equal to 0, and we're in a form we can finally evaluate. So this is just going to be 3 plus 3, and once you've reached a point of direct substitution, you no longer have to write the limit x approaches 3. So this is equal to 6, so our limit is approaching 6. Now for our next example, let's do limit of x approaches negative 2, where we have x squared plus 5x plus 6, all divided by x squared plus 3x plus 2. Now, if we do some direct substitution, we can see we have negative 2 squared plus 5 times negative 2 plus 6, all divided by negative 2 squared plus 3 times negative 2 plus 2. Now, we are going to get 4 plus 5 times negative 2 is negative 10 plus 6, and then negative 2 squared, that's 4 minus 6 plus 2. And you get another indeterminate form of 0 over 0, which means that we're going to have to factor. So let's take limit of x approaches negative 2. Our numerator, x squared plus 5x plus 6, we can think of what 2 numbers multiply to 6 but add up to 5. So you get x plus 2 and you get x plus 3. And then in the denominator, you get x squared plus 3x plus 2. So what multiplies to 2 but adds up to 3? Well, we have x plus 1 and we have x plus 2. So this is going to allow us to cancel out x plus 2 as a common factor, and we get just x plus 3 over x plus 1. But don't forget to write your limit notation as we continue on, because we have not directly substituted in yet. So now we can take our value of negative 2 and substitute it in for every instance of x, where we get negative 2 plus 3, and we get negative 2 plus 1. We get 1 over negative 1, giving us negative 1. Now let's do another example, where we have limit of x approaches 4 for x squared minus 16, all over x squared minus 7x plus 12. So if we attempt direct substitution, we are going to have 16 minus, let's just do it individually first, 4 squared minus 16. We have 4 squared minus 7 times 4 plus 12. So we have 16 up here, and we have 16 minus 7 times 4 is 28, and plus 12, that's equal to 0 over 0, again, indeterminate. So we have to do some algebra. We have limit of x approaches 4 and x squared minus 16. That is just difference of squares, x minus 4, x plus 4. And in the denominator, what multiplies to 12 but adds up to 7, negative 7. So that's going to be x minus 3 and x minus 4. So we can now cancel out the common factor of x minus 4, giving us limit of x approaches to 4, x plus 4 divided by x minus 3. So after this, we can just do direct substitution, where we have 4 plus 4 because we're approaching the value of 4. And then 4 minus 3, giving us the value of 8. So now let's do our next example where we have limit of x approaches to 2 of x cubed minus 8 over x squared minus 4. So direct substitution is going to give us 2 to the power of 3 minus 8, 2 squared minus 4. 2 squared is 4 minus 8. 2 squared is 4 minus 4. So we get 0. This is actually cubed, so that is 8, giving us 0 over 0, an indeterminate form. So we're going to do the same thing. We're going to factor. We have limit of x approaches to 2, and we get x squared plus x power of 3 minus 8. So we can factor this as x minus 2 and x squared plus 2x plus 4. So in the denominator, we can do x squared minus 4 as x minus 2, x plus 2. So we can cancel out that common factor of x minus 2. We just have this. So limit of x approaches to 2 for these two factors. Now, this is a form that we can evaluate. So we're going to do direct substitution. We have 2 squared plus 2 times 2 plus 4 all over 2 plus 2, which is 4 plus 4 plus 4 all divided by 4, giving us 3. Now, let's do one more example. For 5, we have limit of x approaches to -1. We have x power of 3 plus 1 all over x squared plus 4x plus 3. Let's attempt direct substitution. We would have -1 plus a -1 cubed plus 1 all over -1 squared plus 4 times -1 plus 3. So -1 to the power of 3 is equal to -1. We have plus 1. -1 squared is just going to be positive 1 minus 4 plus 3. And -1 plus 1 is 0. 1 minus 4 is -3. -3 plus 3 is 0. That's an indeterminate form. So now we are just going to factor. We have limit of x approaches to -1. And factoring the numerator, we can pull out a x plus 1. And we're going to be left with an x squared minus x plus 1. Then in the denominator, we're going to have x squared plus 4x plus 3. What is going to multiply to 3 but add up to 4? That's going to be x plus 1 and x plus 3. So you can cancel out the common factor of x plus 1, and then you just have x squared minus x plus 1 over x plus 3. So we get x squared minus x plus 1 all over x plus 3. Now, this is a form we can directly substitute into. So we have -1 squared minus -1 plus 1 all over -1 plus 3. -1 squared is 1, and then -1 times -1 is positive 1. Plus 1 is positive 1. All divided by 2 is 3 over 2. We have the limit of x approaches 5 for x squared minus 25 divided by x squared minus 10x plus 25. So we have 25 minus 25 divided by 25 minus 50 plus 25, and this is going to give us an indeterminate form. So we are going to factor our fraction. We have in the numerator x minus 5 and x plus 5 from a difference of squares, and in the denominator we have multiplying to 25 and adding up to -10. Those are going to be x minus 5 and x minus 5. So we can cancel out x minus 5 there. We're left with limit of x approaches 5 for x plus 5 divided by x minus 5. Now we can just directly substitute in. We're going to have 5 plus 5 divided by 5 minus 5, which is equal to 10 over 0. And this is going to not give a finite limit because we have a division by 0. That's going to be undefined. So we have x approaches 5 plus because we can check the sides of this limit. So directly at the point, it may be undefined, but maybe we can see at the sides what's going to happen. So we have x minus 5, that's going to be greater than 0. So x plus 5 over x minus 5, that is going to go to positive infinity. Now, when we are at looking from x approaches to 5 from the negative side, we have x minus 5 is less than 0. So we have x plus 5 divided by x minus 5. That is going to approach negative infinity. So because the sides are different, that means that we know for sure that it does not exist. Now let's do another example. Let's say we have limit of x approaches to 1, x cubed minus 3x plus 2 divided by x squared minus 1. So let's directly substitute in. We have 1 cubed minus 3 times 1 plus 2 divided by 1 squared minus 1. And we have 1 minus 3 plus 2 over 1 minus 1, which is 0 over 0. So let's try x is equal to 1. So that means that x minus 1 is going to be a factor. We have limit of x approaches to 1. We have the numerator can be factored as x minus 1 and x squared plus x minus 2. In the denominator, we can factor this. This will be x plus 2 times x minus 1. Now, we can factor this again. We can take this. Our numerator is not fully factored yet. So x squared plus x minus 2 can be rewritten as x plus 2 times x minus 1. And our denominator is x minus 1, x plus 1, actually. So this is plus 1. Now after this, let's cancel out 1x minus 1. And we're left with the limit of x approaches to 1, x minus 1, x plus 2, divided by x plus 1. So if you substitute in, we have 1 minus 1, 1 plus 2, and we have 1 minus 1 plus 1. So this is 0 over 2, giving us 0, so that works. Now, what about this? We have a limit of x approaches to negative 3, x cubed plus 6x squared plus 9x divided by x squared plus 6x plus 9. So direct substitution, we have negative 3 cubed plus 6 times negative 3 squared plus 9 times negative 3 divided by negative 3 squared plus negative 3 times 6. So 6 times negative 3 plus 9. That is going to give us negative 27 plus 54 minus 27 divided by 9 minus 18 plus 9. That's all 0 over 0. So we're going to factor our numerator and our denominator. Taking this limit notation down here, we can write for a factoring out of x, we have x squared plus 6x plus 9. And then in the denominator, we can write out x plus 3, x plus 3. We can finish factoring the numerator. We have that x still on the outside. We can write that as x plus 3 times x plus 3. And we have x plus 3 times x plus 3. So now we just cancel those. We just have limit as x approaches negative 3 is just going to be x. And if we substitute in, we are just going to get negative 3 as our answer. So for our next example, we have the limit as x approaches 2 for x to the power 4 minus 16 x to the power of 3 minus 8. So if you do direct substitution, we get 16 minus 16 over 8 minus 8 because we had 2 to the power 4 minus 16 over 2 to the power of 3 minus 8. And this gives you an indeterminate form. So let's factor the numerator. We get limit x approaches 2 is going to be x squared minus 4, and we can take x squared plus 4. And then in the denominator, we can have x minus 2 and x squared plus 2x plus 4. So let's continue factoring this. Let's just write out the expanded forms on top. So for x squared minus 4, we can write that as x minus 2, x plus 2, and then we can actually leave that x squared plus 4 up here. Now in the denominator, we can write this as just leaving it like that. So after this, let's cancel out that x minus 2. We are left with limit of x plus 2, x squared plus 4, and this is x approaching 2, we have divided by x squared plus 2x plus 4. So if we substitute in now, we have 2 plus 2 times 2 squared plus 4. And we have 2 squared plus 2 times 2 plus 4. That is 4 times 8. 4 plus 4 plus 4. That's 32 over 12. And we get 8 over 3. Now for our last example, let's do right here. We can do the limit of x to the power 4 plus 2x cubed minus 4x squared minus 8x all over, this approaching negative 2, x cubed plus 4x squared plus 4x. So direct substitution, we get 16 plus 2, negative 8, minus 4 times 4, minus 8 times negative 2, divided by negative 8 plus 4 times 4, plus 4 times negative 2. That is going to simplify to 16 minus 16 plus 16, all over negative 8 plus 16 minus 8, 0 over 0. So that's indeterminate. Let's factor the numerator. So our numerator, we can factor this as x. Taking that out, we have x squared, and then inside we have, or actually, that's going to be x cubed plus 2x squared minus 4x minus 8. Now we can factor by grouping in here. So we have x on the outside still, but then in the inside we can do x squared times x plus 2, and then we can do minus 4x plus 2. Now for our next step, we can take this x, we have x plus 2, and we're going to take x squared minus 4. So after this, we can just factor again. We have x, and we have our x plus 2, correct? And we have an x minus 2 and an x plus 2. So if we just group these factors together, we have an x plus 2 and x plus 2, so we can do x plus 2 squared, and we have an x minus 2 here. So that is for our numerator. Let's talk about our denominator. In the denominator, we have this. So if we factor that, that is going to be x cubed plus 4x squared plus 4x, right? So we get x times x squared plus 4x plus 4. That is x times x plus 2 squared. So then if we rewrite our entire limit with everything, we have limit as x approaches negative 2. So that's equal to, or that's x plus 2 squared, x minus 2 over x plus 2 squared. So then if we cancel out, we have an x plus 2 and x plus 2 squared there, right? So then we just have also an x and x here. We are just left with limit of x approaches to negative 2, x minus 2. So direct substitution, we have negative 2 minus 2. That is negative 4. So overall, for rational limits, what you want to do is, let's review our steps. You want to plug in first. If you get a normal number, then you're going to be done. If you get 0 over 0, this is indeterminate, and then you factor. So then you're going to cancel out your common factor. After you cancel out your common factor, you're going to substitute again. And if you get a non-zero over 0, then you're going to check the one-sided limits. So we can add that if both sides match, that is the limit. And our next case is if both sides don't match. The limit does not exist.